Okay, so now we come to the Michelson Morley experiment. Don't be too worried here about all the math you see on the board. We're just going to do a quick reminder about a few things here, most of which we covered in the math review. But for those of you taking a more qualitative approach to the course, we'll use our Festina Lente motto, as it were, make haste slowly. So we're not going to try to rush through this. For those of you for which some of this is old hat, you can fast forward as you wish, of course. So Michelson Morley experiment, before we do the quick math review or math reminders here, really, the goal of this was to detect the ether wind that pretty much everyone thought should exist. So we'll come back in a few minutes to actually talk about what that was, why they're looking for it, and so on and so forth. Let's just do this quick overview of math reminders, because this really is the first topic that will be more mathematical. But remember, it's all algebra. We'll do it step by step, so that, again, for those of you maybe taking the more qualitative approach, the goal here is to follow along, see where we end up, and understand the concepts involved. And for those of you who like the more quantitative approach, then we can dive into the math a little bit here. So just a few math reminders, notation to start off with. When we have 1 over a just being some number, representing some number, a symbol representing some number, it could be x or b or whatever we want to do there. So 1 over a, we also write that as a to the negative first power, a to the negative 1. 1 over a squared, a to the negative 2 power. Square root of a, write that as a to the 1/2. Square root of a times the square root of a gives us a back again. 1 over the square root of a then is 1 over a to the 1/2 equals a to the negative 1/2, and so on and so forth with things like that. 1 plus a squared clearly means 1 plus a times 1 plus a. You could multiply that out, do the cross multiplication there, and get an answer. 1 plus a to the nth power, where again, n is just some number here. Typically an integer, 1, 2, 3, 4, 5, that type of thing, but doesn't have to be necessarily. That means 1 plus a times 1 plus a times 1 plus a times 1 plus a n times. So if this was 5, it'd be 5 times you'd have to multiply it by. Clearly that gets sort of messy, and in a minute we'll see a way to get around that in certain circumstances. When we're adding fractions together, a over c plus b over d, for example, remember how we use the little mathematical trick? We can multiply to get a common denominator here, so we can add the two fractions together into one fraction. We can multiply each term by 1 in the form of d over d in the first term, so giving us cd in the denominator on the bottom, and then c over c for the second term, again multiplying by 1, giving us dc or cd on the bottom. And so then once we have the common denominator in the there, we can just add them together, so we get AD plus BC over CD. And I just did a little quick example here. If we're doing 3/4 plus 2/5, you can see it works out to 23/20 there. Another thing that we'll encounter form here is if we have A minus B, we can factor out the A from each term. So this would be A times 1 is A, and then A times B over A is just going to be B. The A's cancel. So A minus B is the same as A times 1 minus B over A. Or the form we'll actually see is this, A squared minus B squared. We can factor out an A squared from each term, so leaving a 1 for the first term. A squared times 1 is A squared. And for the second term, A squared times negative B squared over A squared. The A squareds will cancel, just leaving us the B squared there. And before we get to this, then also one other form like this, which this is actually what we will see here in a little bit. Square root of a squared minus b squared. We'll use this little mathematical technique. So factor out the a squared, all under the square root sign. A squared times 1 minus b squared over a squared. Then, if you have the square root of two products, if you have the square root of like x, y, you can do that as the square root of x times the square root of y. So that's what we did here. We have a squared times 1 minus b squared over a squared. So that's the same as square root of a squared times the square root of 1 minus b squared over a squared. And the square root of a squared is just a. And we're assuming here that a is a positive number. We're dealing with positive quantities here. And then that leaves us square root of 1 minus b squared over a squared there. So a little bit of simplification there. So most of that we did in our math review. Something we actually didn't do in our math review that's going to be helpful this time is something called the binomial expansion. We're not going to try to prove this or get into the details of why it's called binomial expansion. We're just going to use it. It's the type of thing that physicists love to use all the time when they can, because it enables us to simplify very complicated expressions. So here's how it works. If you have 1 plus a to the n, so again, this type of situation here, it's 1 plus a times 1 plus a times 1 plus a times 1 plus a. If a here is a very small number, a small positive number, and if we say a is much less than 1, that's what this symbol means, much less than, instead of just less than, it's much less than 1. So a is very small compared to 1, down near 0, but not quite 0. Then 1 plus a to the nth power, this whole thing we'd have to write out, becomes very simple. We can write it as approximately equal to 1 plus n times a. In other words, take the exponent here, whatever that is, maybe it's a 3, 1 plus a cubed, so this would be 1 plus 3a. Or if we have 1 minus a to the nth power, and again, a is much less than 1, it becomes, because we have a minus sign here, 1 minus na. Or even 1 plus a to the negative n power, again, because you're essentially multiplying the exponent times whatever the a value is, assuming, again, a is much less than 1, it's 1 minus na. And this is known as the binomial expansion. So anytime we can do something like that, replace a long multiplication with something simple, and remember, it is an approximation. It's not exactly equal to it, but it's close enough usually for what we want to do as long as a is much less than 1. And in the special theory of relativity, we often have, maybe not often, but we have a number of cases where a here is v over c, a velocity. So we'll see that a we'll have like 1 plus v over c, or 1 plus v squared over c squared, where c is the speed of light, and v is just another velocity. And so in many cases, if the velocity is less than the speed of light, much less than the speed of light, and often is, then we can do this substitution. And it's called the binomial expansion, because we're expanding this out in a series of terms. That's where it comes from. We're actually only using the first two terms. There would be more terms in the series here, but first two terms are usually good enough for what we want to do. Okay, so that's just a relatively brief review, some reminders of the math we'll be encountering. Again, we'll try to take a measured pace here and do many of the steps, so you should be able to follow along. But if you're rusty with some of this, you might want to just jot some of this down, play around with it a little bit, and hopefully knock some of that rust off. So let's talk about just the basic idea here of the Michelson Morley experiment. We're going to break this up into several parts so that if we did this in one long video clip, it'd be a while here. So we don't want to do that. So we'll do it part by part. Okay, first part is we just want to understand, what's going on here. What were Michelson? It was Albert Michelson, Edward Morley, 1880s. Michelson did an earlier version in 1881 of this. The more classic version, 1887, is more precise. He was able to fix up it a little bit in terms of how precisely he was able to measure things. So this is that case for those of you who are interested. Maybe you're in Ohio. It was actually at what became Case Western University in Cleveland, Ohio. And their goal was to detect the ether wind. So to remind ourselves about a couple things here. Remember we were talking about the speed of waves, wave speed, and several key facts about wave speed. One of them, or maybe we'll do two of them here. So when you're talking about wave speed, and of course eventually we're going to apply this to the speed of light, because that's what Michelson and Morley were dealing with, the speed of light. So when we think about wave speed, remember we talked about the movement of the source. So if you have a light source, or we did examples with a source with water waves, a paddle, like in our long tank of water, paddle moving up and down, generating those waves such that what happens to the wave speed then? Nothing happens. It's still whether you're moving the paddle, the source of the waves, through the medium, the water, or the paddle is just standing still and generating the waves, the speed of the waves traveling through the medium, through the water in this case, is going to be the same. Now it does affect, remember, the wavelength and the frequency of the waves, but does not affect the velocity of the waves, the speed of the waves through the water. Same thing with light. If you have a flashlight, some source of light, and you measure the speed of light coming from that flashlight as it goes by you, and then you bring that flashlight, speed up on a truck or something, a very fast jet plane, and you watch it moving by, and then you measure the speed of the light from that flashlight going by. It is not the speed of the plane plus the speed of light that you measure. You still measure just the speed of light as it was. So the movement of the source does not affect the velocity of the waves. But what does affect the velocity of the waves, at least in principle, is the movement of the medium. The movement of the medium does affect the velocity of the waves. And again, the water examples we used, remember, were such that if you have a wave traveling through water, say in a still pond, and you're the observer, you're measuring the speed of the wave traveling across the water, traveling through the water there, you get some value. If you then take the exact same wave and generate it, but generate it in a moving water situation, such as a stream, a river, something like that, the speed of the wave will be the speed of the wave through the water, of course, through the medium, but then also you have the velocity of the medium adding to the velocity of the wave. And so in that case, you will see a difference in the velocity of the wave from the still situation where it's just traveling through the pond, say, or a tank that's still, versus if the tank is moving or if you're in a situation where the river is moving, then the movement of the whole medium, the movement of the water itself, carries the wave along. So if I'm on the bank observing it, I see the water going by faster. And of course, intuitively, it makes sense like that. Or if I'm going upstream, right, then if the wave is going upstream and the water is moving the other direction, then it's slowing down the wave. Okay, so that's the idea of wave speed. And two key facts about wave speed. How does that apply to the ether wind? Well, remember the luminiferous ether was the idea that if light is a wave, it has to have some medium. Something has to be actually doing the waving, the oscillations. And the idea it was the ether. Remember, if you want, you can spell it with A-E-T-H-E-R here if you want, but we'll just use E-T-H-E-R. That's actually how it's used in the multivolume series of Einstein's correspondence. So they chose to use E-T-H-E-R, so that's why I chose to go along with them, but there are many other books that use the A-E-T-H-E-R, so it's not that big a deal. Anyway, so side point there. Movement of the source versus movement of the medium. Let's apply that to light then. Okay, so now we're talking about movement of the medium is the ether. If the ether is sort of the stationary background for the universe, so the universe is just sort of consists of the ether and then everything in it, the Earth moving around the sun and then rotating on its axis as well, so it's revolving around the sun, rotating on its axis. Clearly, as it moves around, it must be moving through the ether. And so that would be like a situation where essentially if I could feel it, if I'm on the surface of the Earth, depending on the orientation, I would feel the ether flowing by me, or I'd really be flowing through the ether, moving through the ether. And so depending on my orientation, if I say, just for the sake of argument, say I was moving through the ether this way, so if I could feel it, I'd feel it coming by this way. But in another direction, I wouldn't feel it depending on my orientation. And so that's what Michelson and Morley set out to try to test a little bit to see, could we determine how we're flowing, how we're moving through the ether wind as the Earth moves around the sun at about 30,000 meters per second, I think is the figure. So we should feel, again, we can't feel it, but if we send a light beam, basically, so here's our light beam, and we're going to send it maybe into the ether wind versus sending a light beam the other direction, maybe with the ether wind. So we'll assume, let's just say, we'll call this the ether wind. And again, that wind is going to be generated just by the motion of the Earth around the sun. And clearly, we're not always going to be directly into it depending on how we're standing and where we are on Earth at any given time, et cetera, et cetera. But you can take all those effects into account. So we'll just do the simplest situation. We'll assume going into the ether wind here, we're either sending a light beam into the ether wind or with the ether wind. And from our basic wave speed fact, the movement of the medium in this case should affect the velocity of the light. In other words, if I'm an observer here, I should be able to detect the difference in the velocity of light depending on which way it's moving in the ether wind. And so that's what Michelson Morley set out to do. And so in the next video clip then, we're actually going to set it up and start doing a calculation just to see what their result was and why it was so significant.